Bugün sistem modellemesi ve sistem simülasyonu konularında çalışan Simoffice ve Navis mühendislik firmalarının işbirliğiyle düzenlediğimiz demiryolu sektörüne yönelik 3 parçadan oluşacak olan webinar serisinin ilkini gerçekleştireceğiz. Siemens'in Simcenter yazılım ailesinden Amesim yazılımı ile mekanik simülasyonlar konulu webinarımıza Siemens'ten Lionel Broglie eşlik edecek. Webinarımız kayıt altına alınacak. Dolayısıyla soruları sunum bittikten sonra webinarın sonuna doğru alacağız. Diğer iki webinarda 3 ve 10 Mart tarihlerinde olacak. Bu webinarların konusu da sırasıyla enerji yönetimi sistemleri ve iklimlendirme konuları olacaktır. Bu konularla ilgili duyurular da LinkedIn ve mail yoluyla sizlerle paylaşılacaktır. Başlayabiliriz yavaştan. Katılımcılar oldukça biz onları toplantıya ekleyeceğiz. Okay, Lionel, we can start. Let me leave the stage to you.
Okay, thank you. Let me first share my screen. This one. Can you tell me when you see my screen?
Yes, we can see.
Okay, excellent. So thank you everybody. Welcome. My name is Lionel Broglia, and I want to really thank you for taking the time to join our webinar focus on the railway industry. So for railway manufacturers and also suppliers, success depends on ability to address increasing complexity in the design and in the design of the equipment, while maintaining an efficient engineering process. So during this hour, I will introduce you some of our solutions using Simcenter Amesim for multi-domain system simulation. But system simulation with Amesim is part of a bigger Siemens portfolio, which allows OEM and suppliers to cover different kind of challenges, such as performance, energy efficiency, such as safety during operation, reliability, and comfort for passenger. So today, clearly, the mechanical topics we will see are part of safety and performance, because we are going to talk about braking system, suspension system, but also it's about performance of pantograph system, and it's also part with system simulation. We can also address some challenges on reliability and durability, and especially on the area of contact between the wheel and the rail, and the shocks which can be generated, and all the vibration in the driveline. So it's important to understand that Simcenter portfolio developed by Siemens allows to consider the full vehicle, the full train or locomotive and so on from different aspects, from a mechatronic system simulation aspect, which is the purpose of the webinar of today, but also from 3D mechanical simulation with multi-body, NVH, acoustics, and so on. CFD as well is part of our portfolio and allows, for example, to perform computational of external aerodynamics, but also thermal comfort inside detailed thermal comfort inside the cabin. And we do have also testing equipments in the area of noise, vibration, and harshness. But again, today we are going to talk about mechatronic system simulation with our main tool called Simcenter Amesim. So Simcenter Amesim is an integrated system simulation solution which allows engineers to simulate and optimize mechatronic system performance. It consists of ready-to-use physical libraries, multi-domain, but also industry-oriented libraries, and I will show you some of them today. Some dedicated to transmission and vehicle dynamics, which is a purpose which will be used today, or batteries and electric machine for the next for the webinar next week, and a dedicated library for heating, ventilating, and air conditioning system, which is the purpose of the webinar in 2 weeks. So Amesim is an open environment that can be integrated into enterprise processes and can be coupled with major CAE tools, control software packages, and can interoperate with functional mockup and be connected with other, of course, Simcenter solutions and as well as Simcenter. Again, today focus will be on mechanical simulation, and I would like to use some user application on pantograph simulation, braking and suspension simulation, and on the mechanical dynamic driveline. So the presentation will be based on customer cases presentation as well as live demo. So let's start with the first topic, braking, suspension, and also pantograph. So how system simulation can support the design of this system is to support the evaluation of static but mainly dynamic performance of all the different systems, the braking system, the suspension system, the pantograph system. It allows to evaluate new architecture at a pre-design stage and identify potential gains, what-if analysis, so considering a certain technology of system and trying to change the sizing of the different components to check what will be the impact on the dynamic performance of the system, and also at the same time on the energy consumption of the system, which can be of interest sometimes. But typically for the braking system, of course, compressor is needed to generate the air, compressed air required for the braking system, and it has a power consumption. What is very important is to be able to have a tool to study this interaction between the different actuators, so they can be hydraulic or pneumatic, and the mechanical structure. And most of the time the system are controlled, are closed loop controlled, and the objective is to provide a simulation platform to be able to couple also with control strategies to validate upfront the control strategies. We'll show you an example on the pantograph. Okay, so let me start with an application example of Waptec Fevlet transport with Amesim on a pneumatic braking system for train. As you can see in the reference, it's quite let's say Waptec Fevlet started many years ago pneumatic braking system simulation with our tool. The interest is to compute, to assess the braking, the transient of building the pressure inside the system to brake the train. So to have, let's say, the complete time response of the system from the command to the braking, it's important to simulate the different elements, the different components of the braking system. Starting, in that case, not from the compressor, because we start with the main pipe with already a 9 bar of pressure inside, but then we have all the pressure reducing valves, the auxiliary tanks, the braking cylinder, and of course the main braking valve, which is presented in the next slide. So as you can see here, the schematic of the pneumatic braking system, and here the associated Amesim model. This Amesim model is created using a specific library called pneumatic component design, and it allows to enter into the detail of the geometry and the technology of each of the pneumatic components. Here it's a relay valve, for example, which allows to, let's say, to set the pressure target in the system in function of a pressure command. And in function of in this system, you have moving parts, you have springs, you have volumes, you have valves which open and closes in function of the displacement of the moving parts. And all this system is represented here using this unitary element, which represents the valve, which represents a piston, which represents a membrane, which represents a spring. And basically, this approach allows to model and simulate any kind of fluid component. In that case, it's pneumatic. It can be also hydraulic, of course. So as you can see here, we have the model of the pneumatic valve with here validation against experiments. The objective of the simulation is to be able to simulate for in service and emergency condition what is the time required to generate the pressure inside the system. So this time transient is what we want to capture with the simulation model and be able to estimate how this transient response will be impacted by the sizings of the components or the operating conditions. Okay? Well, that was the first example I wanted to show you. A second example here is on a suspension system for a boogie. Where we have the possibility with Amesim to represent the damping system, the vertical suspension and damper. So usually this component, this damping can be done using an hydraulic cylinder here with various chambers, and let's say this paper propose an innovative system where, in fact, the movement of the suspension up and down can be damped, but the energy, instead of, let's say, losing the energy of by damping inside an orifice, this movement up and down can be coupled to an to an hydraulic motor coupled to an electric generator to generate some electrical current. So that's the objective of the research project here. I can share with you the paper later on if you are interested. It couples the hydraulic damper with an electrical generator. And the Amesim model allows to estimate what is the electrical current generated by this system, providing the fact that the system has to be damped, meaning that the main function of the suspension is to damp oscillations, and secondary mission, let's say, is to generate also some electricity. Okay, and now what I propose you is to show you an example of a pneumatic suspension in that case. So let me go into Amesim. So as you can see, what I'm showing you here is the Amesim environment, where you have here a sketch where you have the possibility to create your simulation model starting from elements contained in the different physical library here. So here I have, for example, opened the pneumatic library, which is a set of components allowing to define the fluid, what are typical fluids used, simulate, consider sources, ideal sources of pressure, of flow. You have a set of control valve as well, pneumatic relief valve, pressure regulator valves, and so on. of course, linear actuators, but also heat exchange calculation and so on. So all the elements of the pneumatic library are here. And we have used in this example a compressor element, a check valve, an electro valve, and also additional valves to put some compressed air inside the suspension. And here the suspension and the train or the locomotive is represented using mechanical simulation, which is part also of Amesim, in which we have the possibility to simulate either 1D motion, 2D motion, or 3D motion. In that case, its elements are part of the 2D mechanical library. We consider only a 2D motion of the train. Okay, so what is the scenario we want to simulate here? Use the suspension you see on the four wheels is based on a classical spring. But we also add a pneumatic spring, which allows also to compensate the additional weight you have in the train when you have passenger going up and down and going in and out. This pneumatic suspension allows to maintain the height of the train relatively stable. So if we look at the simulation, let me run the system. Yeah, it's very fast because of, yeah, it's the objective of system simulation, and in that case, also the model is a first level of model with not a lot of parameters and dynamics inside. What are we simulating here? We are simulating the fact that after, let's say, 3 seconds of simulation, we add something like 1 ton and 600 kilogram, let's say roughly 20 people inside the train. And of course, due to this additional weight, the spring here are compressed again, and you have a displacement of 10 millimeters. 10 millimeters of the body of the train. Trying to compensate this displacement, we can put some compressed air inside the chambers. So what we do here typically is we with a yellow curve here, we open the valve to put pressure inside the rear left wheel, and as a consequence, the pressure increases in the rear left wheel, and the train lift a little bit to compensate the additional weight we have in the train. And the same after 7 seconds, we put pressure in the front wheels, in the front suspensions, and we have the same characteristic. So that's an example of what can be done using Amesim. Is typically to size the different element of the system, but also to test some control strategies. Okay, that was the first example. Then we come back to the presentation. Oops. Yeah, here. Second example is on pantograph. The example I am showing you here is a result of a research project done by an Italian university, again, some years ago, so as to prove that our technology is very mature and used since many years in the industry. So here it's an example of active suspension. So the objective here is to control here the actuator damper in order to maintain a contact force as constant as possible, you know, because when you are the train is riding, you have the wires which are not at the same altitude, at the same height, and then the system has to compensate this height and maintain the same constant force on the wire. Okay, so in this research activity, they have developed a control system based on an hydraulic actuator and a Moog servo valve. They wanted to control in order to maintain the contact force. And here it's an example of it's part of the model on the hydraulic side, so the hydraulic servo valve and the hydraulic piston. And then the pressure, the signal of pressure, the signal of force are used in order to develop the control strategies. And all the motivation of the paper is to explain the control strategy which has been developed. And as a result, you can see here the validation of the model against experiments for different kind of frequencies, so meaning speed of the train on the track, and yeah, at 0.8 Hertz or 2 Hertz. Okay. So again, it's another example of usage of Amesim for pantograph design. And let's say, starting from this paper, we have tried to create by our own a simulation model which represents more or less what has been done by this university. So let me go now to Amesim again. We can close this one. Okay. So here, you recognize the same icon as in the paper. So there are icons included into the hydraulic library, which is more or less the same kind of elements as you can find already in the pneumatic one. And here the mechanism has been created using the 3D mechanical library. And of course, in that case, the model can be created, let's say, by manually, or it can be generated automatically starting from CAD. There are some documentation inside Amesim explaining the process of generating a 3D mechanical model starting from the CAD. But of course, once the model is created, we have also access to a small to an animation. In our case, the animation model, the animation here. So we did not start from the CAD. So let's say the body represented are quite simple and has been can be automatically generated starting from typically the attachment of the body with the other bodies. Okay. So what are we doing here? We have one main actuator here, which purpose is, you see here, is to push on this arm here, and then to maintain, to put the pantograph close to the wires. Okay, and there is a second one, which is used here to maintain the pantograph in a horizontal position. Okay, so let's first concentrate on the first actuator. So what we do here is that we define a target contact force between the pantograph and the catenary, and then we control the position of the cylinder in order to reach this value. Okay, so let me run a first simulation. Okay, you see simulation running here, and here we can plot the results. Okay, that's done. Maybe I can redo it just to show you that you have the possibility also to update during the simulation your simulation results. So as you can see, we have an initial phase during the first 5 seconds where the train is not moving, let's say. So we have an initial displacement of the piston to compensate the gap between the pantograph and the catenary, and to reach the contact target. So the contact target is 200 Newton, and so we have 100 Newton on each of the point of contacts, because of course we have two catenaires, which are represented here by one body and the other body. Here it's you have the mechanism representing the pantograph, and here the modeling of the contact between the catenaire and the pantograph. So we reach the stabilized position, and then due to the oscillation of the catenaires, which are here more or less 0.5 meter, we see that the piston at the bottom here is moving as well, in order to try to compensate for the displacement and try to maintain the contact force as stable as possible. And we see here, with this set of parameters, we have a peak-to-peak value for the contact force, so peak-to-peak meaning between the minimum value and the maximum value of 38 Newton. Okay, one can say that's good, but let's try to do better. How to do better? We can do it by trying to change some sizing of the system, but we can try also to achieve this with control strategies. Here, in this example, the controller is a PI controller with a proportional gain and an integral gain. So the default parameters are 2 for the proportional gain and 0 for the integration gain. What can be done in Amesim is to perform a design of experiments, okay, with different parameters. So we can set here parameters for the proportional coefficient and for the integration coefficient with this value. We have defined that we want to do a full combination. That means that we will do 25 simulation with all these different parameters. I will not launch the simulation because it will take maybe 3-4 minutes, but I open directly the results. Okay, and the results are the following. What we want to minimize is the peak-to-peak force, and you can see here that we have some minimum peak-to-peak force around 17 here and there as well, and there as well, and it always corresponds to the green value, which is the proportional gain of 5. Remember that we put 2 as default variable, so 5 seems to be a good value independently on the integrator coefficient. You see that there is very limited difference if we have if we have 0 as coefficient for the integration phase, 0.1 or 0.2 or even 1. So let's say that this simple proportional gain can do the job in this example. So it's an example how to use the design of experiment function of Amesim to find an optimum design. In that case, not an optimum design, but more an optimum control. Okay. So that was the second example I wanted to share with you. Let me come back to the presentation now. Okay. So now let's talk about driveline mechanical dynamics. What can be done in 1D, let's say 1D system simulation, is the following: to trying to study oscillations between the, let's say, the power sources of the train. So it can be an electric motor or a diesel engine or a mix. It can be also a hybrid vehicle, but you most likely always have some mechanical transmission, mechanical links between the power source and the wheel set. And this transmission can generate vibrations due to the fact that these mechanical systems are in fact a set of inertia and stiffness and dampers, and by nature have some natural frequency, and we have to check that if these natural frequency are not excited by the power source. We have also the possibility to simulate hunting oscillation phenomena. I will dig more into it in an example later on, but that's basically the fact that you have a conical shape of the wheel. You have the rail, and so you can have a displacement in this direction, and these vibrations can cause some bad feelings, and also some high force during the contact of the wheel and the rail. So we will have a look at an example just after. First example here is more on vibration analysis on the railway drivetrain. So here it's an example of Hyundai Rotem in Korea, which is also using our tool since many years for different kind of applications, mechanical application like this, but also electrical application, fuel cell typically. So the objective here is to understand if you can have some byte vibrations inside the mechanical driveline between the electric motor, the motor reductor, the U-joint, and different coupling elements we have inside the driveline. And all these mechanical structure have their own stiffness, even if they are high stiffness, they are not fully rigid. And that's important to understand if we can have transmission of vibration from the motor to the wheel. Sorry. So here, what you see on the left part of the screen is the associated Amesim model. So you recognize your battery, an electric motor. And then you have all the mechanical elements. In that case, there are 1D rotary mechanical elements, which represent typically mass and spring, spring and dampers on the rotary field. Again, frequency, the natural frequency of the driveline depends on the sizing of the different shafts. It depends also on the gear ratio between inside the system, due also to the U shafts, the universal joints, and so on. We consider not only the stiffness of the different axles, the different arms, but also we consider also the stiffness of the contact between the teeth inside the gearbox. So it can be also important. They are very high frequency, but still, if you have an electric machine which is able to excite very high frequency, it can be important to see if there are no resonances inside the system. So again, we have our mechanical rotary model here, and then it's connected to the wheel set and the vehicle. Okay, so what you see on the left part of the screen is on one side the testing. Sorry for the quality of the pictures, but it comes from the original paper we have, so it's not so high quality. Here we have the testing results, and here we have the simulation results, where we see that we very well represent natural frequency, frequency resonance of about 2 kilohertz, and which is strongly excited. And the interest of the simulation model is to be able to understand which of the elements impact the frequency and the natural frequency of the system. And this is an analysis Hyundai Rotem has performed to check if the sys parameter, typically the angle of the universal joint shaft, or the rolling radius of the wheel, or the clearance between the teeth inside the reducer here, have an impact or not on the vibration. So that's kind of analysis that you can perform. With Amesim and with the 1D model. Now I will show you last example with hunting motion. Okay, directly with Amesim. Let me share again. Yeah, the Amesim model. Here, the model is using a specific wheel set model element, which is part of the powertrain library. You see that we have different elements. We have possibility. We have different coupling elements. You remember maybe the U shaft. Where is the U shaft? Oh, it's not inside this category. Anyway, we have all the possibility to simulate the gears, complex gearbox as well with planetary gear trains and so on. Bearings as well, because it can be important to simulate the losses due to the bearing elements. And we have different kind of vehicle elements. Sorry. Yeah, like this, where we have traditional, let's say, automotive or truck vehicles and pneumatics, but also and tires. But we have also the possibility to simulate wheel set and rail wheel contacts. Okay. By the way, because we have also classical tires, we have the possibility to simulate not only trains but also metros with tires. Okay. So in this example, what we are considering? We are considering the hunting motion. The hunting motion, as I said before, is displacement here in this axis. Which is due to the fact that you have a conicity of the wheel and contact with the rail. Okay. If we look rapidly into the documentation of the elements, okay, I wanted to show you that yeah, you see we have a complete documentation for all the elements that are part of Amesim, which explain all the physics which has been integrated into the sum model. Explain also how the parameters correspond. Here, for example, we have some distances which are explained, and yeah, what we will, and basically, yes, sorry, in this example we will concentrate on the displacement on the y-axis here. Function of the speed of the strain, and then we will see the possibility, of course, to have a look at the contact force here generated by the contact between the rail and the flange here of the wheel. Okay, so let me come back to the Amesim model. I'll plot some results. Okay, they're here. So what we can see here in red corresponds to this hunting motion, okay, in right and left, for actual speed of the train of 35 meters per second. Okay, so we see that in that case, if we give an initial lateral velocity, we see that this motion is damped. Okay, when we are at the critical speed of 41.1 meters per second, we see that there is no damping. We maintain the displacement, the same speed. Yeah, is maintained at the same amplitude. And if we are higher than this velocity. So let's, for example, simulate 45 meters per second. Here it's really critical because you see that we have a divergence and the velocity, the displacement increases. And of course, this is something that we want to avoid, or at least if we are not able to avoid it, is we have to put a flange between after a certain displacement of the axle in this direction. But of course, because the system continue to oscillate, we will stay under a certain displacement, but each time we go into, we will have a contact between the flange and the rail. And in that case, we generate forces, and these forces can be estimated with the Amesim model. Okay, so that's an example of some mechanical simulation which can be simulated using Amesim. There are many more examples, but I wanted to give you the possibility also to share your questions and maybe to ask some on the examples that I have presented to you, and maybe also to ask some additional examples I've not shown today. So thank you for this thank you for your time already, and now I'm open to any question.
Thank you, Lionel.